8.4 and the side splitting theorem. So we're just going to, I'm just going to say what the side splitting theorem tells us. We'll draw a picture and figure out how we're going to use it. It comes from using what we know about parallel lines. So the side splitting theorem tells us that a line parallel to one side of a triangle divides the other two sides proportionally. So it sounds a little bit complicated, but it's really not complicated. So the first thing we want to do, let's remember when we say it's divided proportionally, what do we mean? Do you remember, Remy? When we say we're dividing something proportionally?
It's like the
same fraction. Perfect. So proportionally means same fraction or ratio. The fraction ratio. So proportionally means we have the same fraction or same ratio. So let's draw a picture of the side splitting theorem. And then we can figure out some of these ratios that we get. So there's my triangle. And there's my line. And remember that arrows tell us when lines are parallel. These two have the same number of arrows, so that tells us that they're parallel. So this is the line that's parallel to the one side of the triangle. And what the side splitting theorem says is this divides the other two sides proportionally. So I'm going to label the other two sides, the parts of the other two sides. I'm going to call this the upper left, lower left, and we'll call this the whole left. And I'll do the same thing on this side, upper right, lower right, and that side is the whole right. And I'm going to use abbreviations here when I write my proportions. So WL means whole left, UL means upper left, LL would mean lower left, and so on. So we don't have to keep writing that. So these are our parts of our triangle. The side splitting theorem says this parallel line divides these two sides proportionally. Side splitting theorem gives us a whole bunch of proportions. So I'm just going to write a few of them here. We could write, and I'm just going to write here some proportions. The upper left divided by the lower left equals the upper right divided by the lower right. So this divided by this equals this divided by that. I could say that the upper left divided by the whole left is the upper right divided by the whole right. So when we're making our proportions, we're just matching up corresponding parts. I could say that the upper left divided by the upper right equals the lower left divided by the lower right. And I'll just write one more. The lower left divided by the whole left equals the lower right divided by the whole right. So these are just 4 of the proportions that come out of the side-splitting theorem. We can match up, as long as we're matching up the corresponding parts, we can make fractions out of them, and the side-splitting theorem says that those fractions are going to be the same. So questions about what side-splitting theorem is telling us? All right, so let's look at some examples using the side-splitting theorem. Start with an easy one. So here's our triangle. And there's our parallel line. This is 9, 3, 6, and x, and we want to find x. So we have we have a line parallel to one side of the triangle, divides the other 2 sides proportionally. So we're going to solve this by setting up a proportion. So what's a proportion we could set up? How do we want to set this up, Anna? Okay. 9 over 6 equals 3 over x. Perfect. We matched up this side to this side, the upper parts and the lower parts. Is there another way we could set it up? 9 over 3 equals 6 over x. So we did the parts on this side. So I think those are the 2 easiest ones. And we should come up with the same answer no matter how we set it up, as long as we do it right. We cross multiply here, and I get 9x equals 18. Cross multiply here, and I get 9x equals 18. 9x equals 18, what is x? 2. 18 divided by 9 is 2. So both of these give us x equals 2. So we set it up right, no matter how we set up the proportions, as long as we set them up the right way, we should get the same answer. So these are two different ways we can set this one up. Any questions on that example? All right, let's look at one that's a little trickier. So here's my triangle. Here's my segment that's going to be parallel to one side. And the arrows tell us that they're parallel. This is 3, this is 4, this is 2, and this is x. And we want to find x again. So we need to set up our proportions. Now, on this side of the triangle, what part of the triangle is x? Is it a part of a side or is it a whole side? It's a whole side. So if we set up a proportion, we need to make sure we're using x. We're using the whole side on this side of the triangle. We need to use the whole side on the other side for part of our proportion. So what is going to be our whole side here? 7. Right? 3 plus 4. So now we can set up some proportions. So what would be one of the proportions we could set up here, Tanner? 7 over x equals, so we're matching this one part of this side to one part of that side. So we need to match another part of this side to another part of this side. So what would be our other proportion? We don't know this side, so what are we left with? So we say 7 over x equals 3 over 2. We're matching the whole side to the whole side, and this part to this part. 7 over x equals 3 over 2. So that's one we could set up. Anybody see another one? Another way to do it? Seven over 3 and x over 2. Okay, so we matched the whole side here to this part and the whole side here to this part. So we kind of kept the proportion, the ratios, just with one side. And we should get the same answer. We could do it a couple of other ways, but let's just look at these two. When we cross multiply, I get 3x equals 14. When I cross multiply here, I get 3x equals 14. Same thing. Divide by 3. Divide both sides by 3, so x equals 14 divided by 3. And if I put that in my calculator, I get x equals 4.666 repeating, so I'll round it at 4.67. So this one we had to be a little more careful because one of the parts that we had, the part that we were looking for, was this whole side of the triangle. So we had to find the whole side of this triangle. Questions on that example? All right. One more. This is going to be the trickiest one. And this is a problem. Make sure you pay close attention to this one. This is the kind of problem that tricks a lot of people. So here are parallel segments. The arrows tell us that they're parallel. I'm going to say this side is 2, this side is x, this side is 4, and this side is 6. So now instead of the sides, the parts of the sides of the triangle, I have the base of this small triangle and the base of this big triangle. Now what a lot of people are going to want to do here, the mistake that people make, is they say 4 divided by 2 equals 6 divided by x. And I'm going to put this like this, and I'm going to say this doesn't work. Because what we're doing here is if we do 4 divided by 2, let me draw in with highlighter. When we do 4 divided by 2, we're comparing the sides of these two triangles. When we do 6 divided by x, we're comparing the sides of this trapezoid. So what we need to do is compare this small triangle to this big triangle. 4 and 2 are parts of this small triangle. X is part of the big green triangle. We need to use another part of the big green triangle. So if we did 4 divided by 2, the side of the small triangle divided by the base of the small triangle, how long is the side of the big triangle? The green triangle? 10. The whole side here is 10. So here we're using the parts of the small triangle. We have to use the parts of the big triangle to make our proportion. So 4 divided by 2 would be 10 divided by x. And this gives us, when we cross multiply, 4x equals 20. Divide by 4, x equals 5. So when we have the base of the triangles labeled, we need to make sure we're comparing parts of triangles. And this type of problem is one that people have a hard time with often. Questions on that example? Okay. Last thing we need to talk about today, pretty short notes today, is the side-splitting theorem corollary. Corollary just means a little extra thing that we can figure out. I'm just going to say extra. Just an extra little bit. Side-splitting theorem corollary tells us that 3 or more parallel lines divide 2 intersecting transversals proportionally. So here we have our proportions again. So let's draw a picture of what this corollary is telling us. So we have two intersecting transversals. Transversals are just our lines. If they're intersecting, what does that mean they do? Not necessarily bisect, but are they going to be parallel? No, they have to cross somewhere, right? They have to intersect means they touch somewhere. So here are our intersecting transversals. They have to cross somewhere. So this is our transversal, that's one. And that's another transversal. So let's draw our three parallel lines. We'll just draw three because the side splitting theorem says three or more, so we'll just do three for now. There are our three parallel lines. And I'm going to put my arrows on here to show that these are parallel. And I'll call this L, M, and N. So L is parallel to M, and that's parallel to M. So all three of those lines are parallel. And I'm going to label some points here. I'll call this point A, B, C, and where the two transversals intersect, that's D. And we'll call this X, Y, and Z. So the side-splitting theorem corollary tells us that these parallel lines divide the two transversals proportionally. So all these different parts of the transversals are going to make proportions. They're going to have the same fraction. So this is almost exactly like the side-splitting theorem because we have this triangle here. We just have more parallel parts. We just have more proportions that we can make. So I'm going to write out just a few of them, just like we did for the other part. So I can say that AB divided by BC, this length divided by this length, I have to match that up with the same parts on the other side, XY over YZ. This length divided by this length. AB over AC. So this piece divided by this whole length. Match it up with the same parts on the other side, XY divided by XZ. This piece divided by the whole length there. And let's write up one more. AB will go across, AB over XY. So this divided by this equals BC divided by YZ. So we're just matching up the corresponding parts. Parts in the same place, we make proportions out of them, and then we can use that to solve problems. So any questions on what this corollary, what this extra thing from the side-splitting theorem is telling us? All right, let's look at one example, and then we'll be done. So here's our setup. So we have this shape, whatever it is, divided this way. Maybe it's I guess since these are, I'm going to put these in yards, this would be a field or something. and we want to find x and y. And we're going to say that all four of these are parallel. The arrows tell us they're parallel. So first off, this segment and this segment, are those eventually going to intersect? Could we arrange it somehow where this one is going straight and this one's going at an angle, doesn't intersect somehow? No. So they're going to intersect. So these two would be our transversals. So we're going to have intersecting transversals, and we have four parallel lines. So our side-splitting theorem, corollary, works for this. So we're going to set up proportions. So let's solve for x first. So what proportion, how can we set up a proportion for x? How would you want to set this up, Brody?
Probably 40 over 80.
Does 40 correspond with 80? So if we have this little piece here, what would we want it to correspond with on this side of the...
40 over x.
There we go. We could do 40 over x equals 50 over y. That would give us two variables though. So let's set up another proportion that doesn't have a variable in it. Rather than 50 over y, how about 62.5 over 80? That works. Now I cross multiply and I get 62.5x. 80 times 40 is 3,200. And then I divide both sides by 62.5. And I get that x, when I plug that in my calculator, x equals 51.2 yards. So x equals 51.2 yards. And I can do the problem exactly the same way for y. So what's going to be the proportion that I want to set up for y? What do you think, Zoe? We're going to solve for y now. We can set it up the exact same way. So what am I going to, what's going to be my proportion or my ratio that has y? (50 over y) equals the exact same thing, 62.5 over 80. I can use that. I could use 40 divided by 51.5. I could use that one also, but we know this one works. 62.5 over 80. Cross multiply, I get 62.5 y equals 50 times 80 is 4,000. Divide by 62.5. And I get y, when I plug that into my calculator, equals 64. So I solved this problem again by setting up proportions between the matching sides, the corresponding corresponding parts in this case, and solving the proportion by cross multiplying. So I'm hoping that we're starting to see that that cross multiplying, setting up proportions, cross multiplying, a big thing in this chapter. It's really the main tool that we use when we talk about similarities, setting up these proportions. Any questions before we finish? Okay.